A curious mind. In the quiet English countryside of Woolsthorpe, a young Isaac Newton sat under an apple tree, lost in thought. It was the 17th century, an era of scientific awakening, and Newton's mind was brimming with questions. What made objects fall? How did the planets move? These were not mere passing thoughts, but the seeds of discoveries that would transform human understanding of the world. From an early age, Newton displayed an insatiable curiosity. His mother hoped he would become a farmer, but his fascination with nature and numbers led him to Cambridge University. There, amid books and experiments, Newton embarked on a journey that would change the course of science forever. At Cambridge, Newton was greatly influenced by the works of Galileo, Descartes, and Kepler, all of whom had laid the foundations for a new way of thinking about the natural world. The apple that shook the world legend has it that an apple fell from a tree and struck Newton, prompting his groundbreaking thoughts on gravity. While the truth may not be as dramatic, Newton did indeed ponder the force that pulled the apple to the ground. He realized that the same force governing the fall of objects on Earth extended to the heavens, keeping the moon in orbit around Earth and Earth around the sun. This led to his formulation of the universal law of gravitation. According to Newton, every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. This single insight united celestial and terrestrial mechanics, a feat no scientist before him had achieved. Newton's calculations explained why planets followed elliptical orbits, confirming Kepler's earlier observations. However, formulating these ideas was no easy task. Newton worked tirelessly, refining his theories through rigorous experimentation and mathematical proof. It was not until years later, when Edmund Halley visited him in 1684 and asked about planetary motion, that Newton finally compiled his findings into a coherent framework: the three laws of motion. Newton's fascination with motion led him to define three fundamental laws. 1. Law of inertia. An object remains at rest or in uniform motion unless acted upon by an external force. Second law of acceleration. The force on an object is equal to its mass multiplied by its acceleration. F equals ma. Third law of action and reaction. Every action has an equal and opposite reaction. These laws explained why planets orbit the sun, why cannonballs fly in arcs, and why objects fall at different speeds depending on their mass. They became the foundation of classical mechanics and revolutionized physics. Before Newton, many believed that an external force was required to keep objects moving. His laws debunked this notion, showing that motion persists unless interfered with by another force. Newton's laws were not just theoretical. They had practical applications in engineering, military science, and space exploration centuries later. The motion of rockets, the design of bridges, and even the understanding of car crashes all rely on his principles: the prism and the nature of light. While Newton was revolutionizing mechanics, he was also investigating the nature of light. In a groundbreaking experiment, he passed sunlight through a glass prism and observed that it split into a spectrum of colors. This refuted the prevailing belief that white light was pure. Instead, Newton proved that white light was composed of different colors, which could be recombined to form white light again. His work on optics led to the invention of the reflecting telescope, which used mirrors instead of lenses to eliminate chromatic aberration. This telescope was more powerful and compact than traditional refracting telescopes and became the foundation of modern telescopic designs. Newton's contributions to optics went beyond simple observations. He theorized that light was made of tiny particles, a hypothesis that contrasted with the wave theory of light. Though later experiments would refine our understanding of light, Newton's work laid the groundwork for future discoveries in physics and astronomy. The Principia, a masterpiece of science. In 1687, Newton published his magnum opus, Philosophia Naturalis Principia Mathematica, or simply Principia. This monumental work laid out his laws of motion and gravitation, providing mathematical proofs for Kepler's laws of planetary motion. The Principia was not just a scientific work, it was a declaration of the power of human intellect. It demonstrated that the universe operated on predictable laws, and with mathematics, one could unlock its mysteries. This work cemented Newton's reputation as one of the greatest scientists of all time. Newton's Principia faced resistance at first, as not everyone was ready to accept a mechanistic universe governed by mathematical laws. However, the undeniable accuracy of his predictions won over even the most skeptical critics, establishing Newtonian physics as the dominant framework for centuries. The alchemist and the mathematician beyond physics, Newton dabbled in alchemy, believing that metals could be transformed into gold. While his alchemical pursuits never bore fruit, they fueled his meticulous approach to experimentation. Newton was also a brilliant mathematician, co-developing calculus alongside Leibniz. His version, known as the method of fluxions, allowed scientists to analyze motion and change with unprecedented precision. Calculus was revolutionary, providing tools that would later be used in engineering, economics, and physics. The controversy over whether Newton or Leibniz invented calculus first sparked a bitter feud that lasted for decades, with their respective followers engaging in heated debates. The later years and legacy Newton later became the president of the Royal Society and was knighted by Queen Anne, becoming Sir Isaac Newton. His later years were spent refining his theories, mentoring young scientists, and overseeing the British Mint, where he revolutionized coin production. As master of the Mint, he took a hands-on approach, even personally investigating counterfeiters and bringing them to justice. Despite his scientific achievements, Newton was known for his intense secrecy and solitary nature. He rarely collaborated and was often embroiled in disputes with fellow scientists. His disagreements with Robert Hooke and Gottfried Wilhelm Leibniz are well documented, but they did not diminish his scientific impact. Newton's discoveries continue to shape modern science. His laws of motion paved the way for engineering, his work on light led to modern optics, and his theories of gravity helped Einstein develop relativity. Newton's legacy is not just in his equations, but in the spirit of inquiry he inspired in generations of scientists. The lasting influence on science and beyond Newton's influence extends far beyond physics. His work inspired advancements in astronomy, engineering, and even philosophy. His belief in an ordered universe, governed by laws that humans could decipher, influenced thinkers during the Enlightenment. Today, space agencies use Newtonian mechanics to calculate satellite orbits, and his principles continue to be fundamental in scientific education. Even as new theories such as Einstein's relativity have refined our understanding of gravity, Newton's laws remain incredibly useful for practical applications. Every modern engineering discipline, from aerospace to robotics, still relies on Newtonian physics. Conclusion. A mind that defined an era, Isaac Newton was more than a scientist. He was a visionary who unlocked the universe's secrets through sheer intellect and perseverance. His story is a testament to the power of curiosity, discipline, and the pursuit of knowledge. Newton once said, "If I have seen further, it is by standing on the shoulders of giants." Yet, in reality, it is he who became the giant upon whose shoulders modern science stands today.